Thank you very much, Simon. And good morning, everyone. Happy May Day. And thank you again for the invitation to speak. So there's a handout that I hope you have from the back of the hall or from yesterday, which amplifies the slides. So hence the numbering 6, 7, 8. This is very much a sequel to what was said yesterday, and let me begin by just that's good. We'll do it this way by discussing the story so far. I wanted really to emphasize that there's two ways in which underdetermination in cosmology is a bit different from the standard philosophical discussion. One was that it isn't so much grand theories that are underdetermined by the possible observations as the choice of model of a given theory. So the overarching self-denying ordinance of this pair of talks was to consider what the cosmologists would call the standard model, not in the modern sense of the last 10, 15 years, but in the sense of the 1970s. So I'm really wanting to try and talk about the philosophical aspects of cosmology from the history of the universe from about 1 second onwards. So primordial nucleosynthesis, yes, but much earlier than 1 second, especially inflation, not here being discussed. So I am concerned with the accepted overarching theory of general relativity applied in a cosmological context and quantum field theory on a curved space or space-time. That's the established theory about which we're interested in the discrimination by observation of which model to adopt, where model, of course, is a very overused word, but it means, of course, something like a solution of the theory in physicist jargon, or a possible history of the system in a more general jargon, and it means a possible world in the philosopher's jargon. And of course we'll never know the detailed history of the cosmos in all its myriad detail, or want to know, a topic that came up when the aliens landed to deliver many encyclopedias to David Wallace in his discussion period yesterday. So it's not as if we even want to know the myriadly complicated microhistory. The thought then is that we want to know the main features of concern in terms of our concepts, and it's a matter of discriminating those features on the basis of observation. So it's the underdetermination of theoretical hypotheses by data, the underdetermination of which model represents the main features of cosmic history by all possible observations, and the exigencies of collecting the observations in one place, that is to say, in one cognizing mind, or idealizing at one space-time point. It's those matters that were center stage in the second half of yesterday with the report of a discussion, a theorem and discussion by John Manchak. Okay, so that's the story so far yesterday, and the qualification that I announced on the earlier slide is that this standard model, in my sense, is not established beyond doubt. So philosophically, here, I admit, in the broad philosophy terms, we are looking at business as usual. This is underdetermination of overarching theory, one rival, another rival, a third rival. It is in fact true that although there is a standard model that is now often, that word is used for a model much more elaborate than that of the 1970s. It was called the standard model then. We'll discuss it in a bit more detail when we talk about the cosmological principle. Now it might be called the lambda CDM model because it has lambda the cosmological constant representing dark energy, and CDM for cold dark matter. So the lambda CDM model is, I'm saying, not established beyond doubt. It is, so there are rivals, in particular spherically symmetric but inhomogeneous models of the Lemaitre-Tolman-Bondi type are in the literature as able to be fitted to the observations so far. So I know nothing of this, but it should be registered. But it certainly puts us back in the philosophical business as usual. So at the general level of a philosopher, it's business as usual then. Okay, so there's another qualification on your handout, but I won't say it out loud. Let's talk about the cosmological principle. This is divided into 3 subsections, which I called consequences and reasons and evidence. And the overarching story is that it is a lucky break, or rather a lucky break so far. I won't deny it. I'll give reasons for it. But these reasons look like they could peter out tomorrow. Okay? So that's the lucky break. But it's also a lucky break, not just in terms of evidence, but in terms of more general features or reasons. So it's a lucky break in the sense that it has beneficial, elegant, strong consequences for your description of the universe. That's in consequences. And then there are reasons for it which are worth pausing over. That represents essentially theorems relating its notions which reduce what you would have to observe in order to confirm it. Right? And then finally there is the evidence. So in any case, I haven't stated it. What does it say? It says that on sufficiently large scale, the matter and the metric, so the matter and radiation in the universe and the metrical structure are both spatially isotropic, no preferred direction in space, and also homogeneous, the same from one point to another. And it was articulated in the 30s, and it has, as exhibited here, strong consequences. You'll know FRW for Friedman, Robertson, Walker. So between Friedman's papers of 22, 24 and Robertson and Walker of the mid-30s, the analysis of the role of large assumptions about global uniformity in space-time this sort of analysis was conducted, and it led to that half dozen or dozen or 20 models you'll find in your exact solutions chapter of your cosmology textbook. And summarizing, what it means is that there's a cosmic time function whose simultaneity surfaces foliate the space-time, and that the entire space-time geometry is described just by what K, and this is exactly Roger Penrose's K, either 0 or +1 or -1. And then what fills the rest of your cosmology textbook, the details of RT, representing the scale factor, or for, as a bit of a metaphor, the radius of the universe, whose evolution depends upon the matter and radiation. So that's what actually leads to the variety of the models and fills your cosmology book. The thing I want to emphasize is that it's got an allowance for changing spatial geometry. I said the cosmological principle is a statement of spatial isotropy, not space-time isotropy. It's at a top point in time, there's spatial isotropy, and there's an allowance of a cosmic time function, and there's an allowance of a changing universe, an evolving universe there. So in particular, expanding. So, I mean, you could go on for hours really singing the hymn of the our good fortune and the lucky break, but you will know from yesterday, if not before, that Einstein introduced the lambda to get a stable universe that didn't implode. So he wanted to have an anti-gravitational force to balance the implosive tendency of gravity. And of course, this is his biggest blunder, but indeed a happy mistake, as Roger said yesterday. But there's the lucky break as well that Hubble came along, discovers the expansion of the universe in just the decades that these analyses provide a geometry or mathematical description for it. Okay, so that's the consequences. Now, the reasons that I promised you are things like theorems that, in effect, you could say they're consequences or they're sufficient conditions, if not necessary conditions for the principle. They're theorems that relate the concepts and reduce what you would have to observe in order to get evidence for it. So what I've put here on the slide is just towards the end of your handout. I didn't put everything on the slide. The beginning of your handout mentions that if you disregard matter fields and talk only about geometry, there are theorems you'll find in the textbooks like Weinberg or Hawking and Ellis, which relate homogeneity and isotropy. For example, there is the obvious remark that if homogeneity is the equivalence of all points on a spatial, on a simultaneity slice, and isotropy is a remark about spatial no preferred direction at a point, then if you are homogeneous and you are spatially isotropic at just one point, then you are spatially isotropic at all points, as required by the CP, right? Because I said it was homogeneous. So if there's spatial isotropy at one point, there'll be spatial isotropy at all the other points. Another slightly more interesting remark is that if you have isotropy at all points, then you will have homogeneity. And the intuitive idea is that if you have 2 points in a manifold that's connected, you can connect them, map one to the other, by a sequence of rotations centered around various other points. So if you imagine perversely going from A to B, not in a straight line or a near straight line, but by a ballet-like sequence of rotations about a judiciously chosen sequence of intermediate points, well, the isotropy at the various swivel points en route will secure the equivalent. So there are statements like that, and there are statements which you'll find in the textbooks, or maybe the handout, I forget now, about the role also spherical symmetry enters into some of these theorems. But there are other theorems that relate these conditions of the CP to the matter fields, and one famous theorem is the EGS theorem of 1968, that if the matter is pressureless and the radiation is spatially isotropic about each point, then the CP holds. And that means that the metric is spatially homogeneous and it's spatially isotropic, and therefore it is FRW. And there are 2 extra comments to make about this. One is the cosmic background suggests that the radiation is isotropic around here. And this Copernican principle that came up in discussion yesterday, that our position should be typical, suggests that if we see the radiation to be isotropic, then so does everybody. And so you can support the antecedent premise there, radiation isotropic about each point, by this sort of argument. I should add, though, that as philosophers of cosmology would know, there is a long tradition in the mid-20th century in philosophy of cosmology about rather rationalistic defenses of things like the Copernican principle or the cosmological principle. And they're not, I think, completely compelling. And so I'm really taking a rather low-key attitude to those. If you look at Helga Krag's book called Cosmology and Controversy, a history of cosmology from 1915 through to 1970-ish, you'll come discussing the Big Bang versus the steady state. There's a lot of coverage of the literature about the slightly rationalistic arguments that were put forward. And those of you keen on the history will know that, of course, the steady state was denying the evolving universe, and it had something that clearly sounds better than today's topic. It was called the perfect cosmological principle, which precisely denied that there would be the genuine evolution of the large-scale structure of the world. So there is a background here of my probably falling in with a widespread tendency to be suspicious of the rationalistic tenor of the arguments of the mid-20th century and the early decades of the philosophy of cosmology. And then I'm grateful to George Ellis for pointing out to me that there are theorems, in particular a recent theorem by Clifton and co-authors, which avoid making assumptions about all or even many space-time points. And they're therefore less reliant on this typicality idea that what we see should be typical. The so-called Copernican principle. So there's a Sunyaev-Zeldovich effect, which is exploited in their analysis to argue that if over time you look at the CMB, then you can in principle conclude that your past light cones metric is homogeneous and isotropic. And that last phrase really leads into the next section called evidence, because so far I've argued up the prospects for the CP on the grounds that it's a good thing if it's true, that's the consequences, and it might not be so hard to know it's true. That's this section called reasons, about mathematical theorems that reduce what you'd have to know in order to have a warrant for believing it. But of course, you'd expect the warrant for believing such an empirical proposition lies essentially in the evidence. So we now go to 7.3, the evidence. And as emphasized yesterday, our evidence lies in our past light cone. Hence this phrase at the bottom of the left side. So here's the lucky break. Not just in the 1920s, but over the 80 years since, with the addition of our observational powers of all sorts of wavelengths other than the optical, and with a greater depth of penetration, spatial range of observation, it holds up. It holds up provided you average over length scales larger than those structures that you have in yesterday's deepest observations, but in today's medium range observations you can see. So the galaxies are clustered, and there's talk of superclusters, though I understand from some cosmology friends that this is overdrawn in order to get more funding for yet deeper surveys. If one looks at length scales larger than 300 million light years, it is holding up pretty well. There's a lot of philosophy here, in a way, if one wants, about the nature of idealization. And we'll come to that a little bit at the end when I mentioned that inhomogeneities represent a threat to the cosmological principle. So much for coming to believe that it holds true of our past light cone. What about the truth of it overall? Because it's a statement about the entire universe. That's to say, space-time. So it's not about our past light cone. And I couldn't resist the St. Paul phrase, because I believe that's what Joe Silk and John Barrow do. They look through a telescope, so in the night, and so this metaphor just was too good to not grab. The bad news then, after the lucky break, is that our past light cone is a small part, much less than all. And as I said in answer to David Wallace and Chris Timpson yesterday morning, enumerative induction is risky. That's at the bottom of this left side. There are various ways. There are various regions of space-time going beyond the past light cone of Earth now, to which you might make an inference, not just about the CP, but about other propositions. And there are three: the causal past of our cosmic time slice, assuming there is a cosmic time function; the causal future of the observable universe in my sense of past light cone of Earth now, as I said, truncated perhaps at time equals 1 second or time equals 10 to the minus 11 seconds. At 10 to the minus 11 seconds, we begin to doubt that the standard model would apply. The standard model, that is, of high energy physics, so that that's another natural place to stop belief in your friendly neighborhood cosmologist's latest proposal. And then there's the entire space-time manifold consisting of all the points that are topologically connected to Earth now. So obviously 1 and 2 are subsets of 3, and broadly speaking, 1 and 2, neither is in the other. So all these are vast. However, exactly we go earlier than 1 second, and they're all much faster than the past light cone of Earth now, however we extend the standard model. So I just wanted to make vivid that there's an issue of knowing our neighborhood, that is past light cone of Earth now, knowing it being hard to know beyond, and it's hard to know more or less whatever you say about the very early universe. So this is everyday situation for the practicing cosmologist, but there's a lot of gee whiz actually about popular discussion of cosmology, which might make the philosopher coming into it think that all the controversy or all the philosophical issues or all the reasons to be a bit cautious only lie with the physics of the before 1 second and its aftermath in the later universe. But it's not quite as simple. I mean, there's more to pause over even about these matters. So the result is, of course, that there is efforts to argue for the CP by a dynamical argument, and this came up in discussion yesterday. Surely we should adopt a theory in that grand sense I was discussing, and argue that generic initial conditions would evolve to a geometry which is approximately on large enough scales, got the properties of homogeneity and isotropy. And initially, I think it would be fair to say that the chaotic Misner, the chaotic cosmology of Misner, or the mixed master universe of Misner of the mid-60s, was a good example of this. And in fact, analyses by John Barrow and others showed the limitations of that program. Now, the leading framework for undertaking the right-hand page program is, of course, inflation. And three or four general issues arise. And in particular, the A and B are broad philosophical. C is a remark about this meeting, and D is a remark about, in effect, future meetings in this project. What counts as an explanation, especially in relation to features of the universe as a whole? And again, perhaps I could echo what I was talking about mid-20th century philosophy of cosmology as having rationalistic arguments that I didn't thinks so highly of. I want to also mention that there was agonizing or anxiety then about what it would be to have cosmology, since it was a science with only a single object, namely the universe. So how could there be laws of cosmology? And again, I take a rather low-key, happy nevertheless attitude about this. I think, and again, I think I'm being perfectly kind of orthodox. It's the natural reply is to say, to be sure, cosmology is applied physics, so it's a historical science. But you can still, in a sense, speak of laws of it. It's the laws of general relativity or quantum theory applied either on very large scales, especially general relativity, or on very small scales, early universe, especially the quantum end, because these are laws of cosmology in the sense that they're laws of these general theories applied in a context that's relevant to cosmology. So I don't think there's a problem about laws of cosmology. It's not as if one has to have the universe itself as the object that is the instance. Okay, so issues about what counts as explanation. Also, there is the question, take what a philosopher would call a particular proposition as against a universal generalization. So it's not of the form for all x, blah, blah, blah. It's a particular proposition, such as initial conditions. We Humeans believe that laws of nature are generalizations that are contingent, but not just any old true contingent generalization. So they are an elite minority with special features for encoding a lot of information about the way the world works. We can discuss that, what it will come to. What does it mean, encode a lot of information? But for somebody who's a Humean, the laws of nature are contingent. So are initial conditions. So there is a question, in what sense, if any, are particular propositions such as initial conditions more contingent or more a matter of mere happenstance than are the laws of nature? And does one need such a stronger sense in order to make the explanations of subcontinent A attached to this sort of program? The CP is by no means the only feature of the late universe for which this effort is undertaken. Of course, the topic of this meeting, arrow of time. And finally, the issue of measure. Not every initial condition is going to evolve. No doubt. We have to be modest. It will certainly be true that not every initial condition of our theory will evolve to a later scenario with the desired feature. So we have to ask what is a typical initial condition, or to introduce measures and talk about with high probability. Okay, so final slide, actually. We're going to have a nice long coffee break. The two issues that Ellis, in the paper cited there, brings out in a survey of inhomogeneity in cosmology. There are three issues that he discusses. I just picked two. The third issue is about how inhomogeneity may affect observation and therefore how we interpret the observations we in fact make. Here is a general point about the difference between macrodynamics and microdynamics. What we've been discussing is the putative macrodynamics of an FRW model that's expanding. And locally, on scales less than 300 million light years, especially very locally, matter and geometry are inhomogeneous. The question therefore arises, this goes back to the topic of idealization, can we show that the coarse graining, by taking larger spatial volumes, really does rub out the inhomogeneity and induce the macrodynamics we're looking at? And this is, I've written there, just a very difficult question to answer. And if you read the Ellis paper, you'll find there are 4 frameworks for discussing it that have been explored over the decades that he gives a summary discussion of. The general point for a philosopher is this idea of the meshing of micro and macro dynamics. There's really, in a way, 2 points here at a general philosophy level. One is the commutation of the arrows in a sort of algebra-like sense, that if you have the macro and you have the micro, and you have a state space then, as it might be S here, and, well, let me call it S here and S bar here, and the point is that this state space is partitioned into cells, and the cells of that partition are the elements of S bar. So this is just projection, right? Canonical projection. And time evolves. With time you have dynamics. We're given actually in real life a microdynamics. One envisages that the universe has a microdynamics. This is the theory we truly believe of the detailed structure of the universe. As this time evolves, individual points get sent to wherever they get sent to, and it might be deterministic in particular, and the question arises whether 2 points in the same cell, this one and this one, do they in fact end up in different cells? If they do, then the deterministic microdynamics has not induced deterministic macrodynamics. And pilot wave enthusiasts will recognize that this is exactly what they think is going on in quantum theory. Right? There's a microdynamics of the pilot wave, which induces, by the coarse graining that gives you that slovenly, intellectually lazy thing called orthodox quantum theory, the indeterminism of the collapse of the wave packet in measurement. So that kind of commutation of coarse graining with time evolution is the main topic. As Ellis emphasizes, it's compatible with there being a commutation of this diagram, that the look of this dynamics is conceptually very different from the look of the microdynamics. And actually, that's more the bread and butter of what's discussed in those 4 frameworks that he surveys. Right? I should mention there's also actually a converse question to this, does the microdynamics coarse grain to give the macro? And that is the kind of thing taken up in recent work by Giolini and Carreras as a Super Reviews Modern Physics 2010 article, which is concerned with the question, how, if at all, does the cosmic expansion affect local dynamics? And you'll remember that the image of the inflating balloon with the galaxies on it was sometimes said that the galaxies are pennies glued to the balloon. And the real question is, how rigid is the glue? And in fact, Chris Smink, an excellent philosopher of cosmology in Canada, has a good joke about this, because I think it's in Annie Hall that the young Woody Allen growing up in Brooklyn has a real crisis, existential crisis, age 12 in about 1935, because he's heard on the radio that the universe is expanding. And I mean, that's deeply worrying, as it should worry us now, right? We have to kind of refresh, get back to those states of naivety before we were soft-soaked with our physics and philosophy education. Yeah, it's worrying. So there he is, quaking in his Brooklyn apartment, and his mum tells him, well, whatever his name was, Alvin or something, Brooklyn isn't expanding. And so the point is that she's right, you know. Locally, the dynamics is not affected, and so there's a good question about to what extent isn't it affected, and And there's an analysis of that by Giolini and Carreras in 2010 on the archival reviews of modern physics. But that's rather the converse of what this is. Okay, so finally something of which I know nothing, but others in the audience do, so I'm glad we have masses of time for question. Being the best fit among a group of models doesn't mean you're the unique best fit in a larger class of models. And so the lambda CDM model, well, the version of it that takes the specific choices of 73% lambda, 27% cold dark matter and baryons. That particular version is the best fit, but it's not the unique best fit. And so there may be these other inhomogeneous models. So let me invite discussion while saying that I have in this talk been following in the footsteps, not just of the likes of George Ellis, John Barrow, Joe Silk, whose writings were so inspirational, but especially Oxford cosmologist turned philosopher Klaus Weisbart, who was indeed, I think, Joe's postdoc. So thank you very much for your attention. Well, I saw Joe, then Nazim, then Lady Between, and then David. Yeah, I guess so, yeah. I'll see how flustered I get, yeah.
Okay, so I'd like to just stress that there's a fundamental difference, really, between the way a philosopher and a physicist approaches some of the issues. I'll give you a couple of examples. Does these alternative models, such as the metric-Tolman model, is that a good match to the universe? Now, we work with phenomenology. We don't have a fundamental understanding. Lambda CDM, we don't know what lambda is, and we haven't measured CDM. It's a total mystery. But, we stick in a couple of parameters, and one can explain a vast amount of phenomena. It's a working model. It's not a fundamental theory. Maybe someday it will become one, okay? But it's not yet. And so one has to compare this with the other things in the market. And you're given some examples. And from the physicist's point of view, these are very, very bad examples. Now, I don't know how you can assign a quality rating to your different categories, but if you try to fit the metric-Tolman bonding model to the universe, you'll find there are numerous problems. You can't conclusively say it is wrong, but there are many, many reasons that tell you it's almost certainly wrong. And most of my colleagues, 99% of them, I would say, would not work on that because they know it'll take them nowhere. But there is a 1% that definitely pushes very seriously. And the philosopher, I'm afraid, has a tendency to give those papers equal weighting to the others. And this is not such a good thing to do, I think. Well, at least one has to be aware of this issue. And getting back to micro versus macro, again, there's, to me, a very compelling argument. It's true the universe now has horrible microdynamics, very complex. And there could be some weird back reactions that affect the mathematics. But if you look at the sky in the microwave back radiation, you see the universe as it was 300,000 years after the Big Bang. Incredibly simple, perfectly linear to 1 part in 100,000. Now, it's very hard to believe that if your fluctuations are 1 part in 100,000, taking some higher power of them to give you back reaction effects would have any effect whatsoever on the expansion or the acceleration of the universe. Yeah. And that's what most people have demonstrated more rigorously than that statement goes. Yeah. Of course, again, there's a minority that will claim that, well, and they could be right, but there's something else in the calculations that's missing. We have to consider a larger space, perhaps, or other initial conditions, perhaps, which may make that wrong. So,
but what is it? What is it that I totally, sitting at your feet on this, and I agree in particular with your first comment. So this was a little bit of the maverick, just tossing in the heterodoxy, but glad to be told, look out, it's only 1%. But what is it about? What is it about the extreme smoothness at the last scattering surface that is successfully described by orthodoxy and not successfully described by...
It's more issues of back reaction. People
Right.
are worrying about back reaction, and now that could, in fact, account for acceleration, etc., to do away with dark energy. And that involves some higher power, really, maybe the square of their local fluctuations.
Right.
And if things are truly linear, it's very hard to imagine. Now that it could still be divergence on very small scales, which you don't. Which you
I see what you're saying.
And things could come in there. If there are infinities hidden away somewhere, then my argument is completely wrong. I agree. But that's the loophole in the whole problem.
Right. I see. Thank you. Yeah. Well, Nazim. Yeah.
I have a question about the novel ways of in the underdetermination, that we started with, and the idea of distinguishing between theories and models. I have the impression that one may argue that we may have a similar situation, let's say in physics, where we have the standard model of particle physics, but we are not testing theories. We don't have answers to questions like why chromodynamics is described by SU3, why we use these specific gauge groups, why we don't use exceptional groups. We don't have answer to these questions from the perspective of the standard model of particle physics. So maybe we have an underlying micro dynamics, call it string theory, whatever. We will never have access to these micro dynamics. So I'm not really understanding in which sense the theory model distinction in cosmology is novel. And then I have another question about the CP from the point of view of if we believe in eternal inflation and string theory landscape, because you distinguished between our past lightcon, future lightcon, and then topologically connected manifolds. So I'm just wondering if you are considering eternal inflation. I don't understand Linde's argument, but are you claiming that the entire manifold topologically connected is this big, huge landscape of multiverse? Or
Well, the short answer is to the second question, and that. So let me say this: my idea was sheer agnostic allowance that it may well be that complicated early regime makes for region I call Little Roman 3 much bigger than Little Roman 1 and Little 2. So there's just an allowance thing there. But the first question, this is in a way related to the landscape business. It goes back to my being a philosophical Humean. Broadly speaking, the Humean is the person who says that explanation has to stop somewhere, and go as far as you can, but you must expect to stop. So I can imagine, never mind gravity, just thinking of high energy physics, that human inquiry would end with discovering that, U1 times SU2 times SU3 is the true theory of the non-gravitational, and that's that. And, you're not going to get a deeper explanation as to why not exceptional groups. So there's a kind of, low-key answer. I think human inquiry, even if, well-funded and even if superhuman, even David's aliens may be stuck with the kind of Humean bedrock explanation must stop somewhere. That's my Humean perspective on it.
Is it then correct to say what we are assuming to be novel is not really specific cosmology, it's mainly related to the fact we don't understand the details. It's similar to particle physics, but we don't understand.
Sorry, yes. Now, I remember this was another theme of your first question. You were suggesting I was saying that in cosmology the theory model contrast is different. I think I don't want to put it like that. I think there's a theory model contrast which is pretty much the same in different sciences, except that both words are vague, and within a science for example, you'll get theory used in different ways and model in different ways, even within a science. So, but I did want to say that this particular topic of CP, it's model. It's natural to say that it's the model that's underdetermined, because we're working with an accepted background ground theory, namely general relativity and quantum theory, combined on scales where we feel it's safe to do so, and sometimes each used alone. Sorry, I hope that's an answer. Okay, sorry, you had a question, and then David, and then John Barrow? Yeah.
It was just to take Joe's comment a bit further as well, that this idea that, you know, we could be living in this dimensional common body sphere. In the last 5 years, we've got so much more data evidence that just says it's incredibly unappealing and new things rule it out. And, you know, as Joe said, there's a minority who work on it because most people think it's just very ugly, but the minority who are working on it have increasingly said this is not feasible. So I think cosmologists always trying to find things that don't fit down to CDM, but we just haven't really managed so far.
Right. Okay, thank you. Well, this is, yeah, it's an Oxford tutorial here. I'm sorry, at everybody's expensive time and my monetary free. So, David.
Okay, and I can't resist, I've got a question. I can't resist to the quick treacherous comment to support Joe's point more broadly. I think this kind of 99%, 1% things that bad happen in philosophy of physics generally. I think the 1% could equally be the very bone theory or algebraic QFT or loop quantum gravity. Anyway, the question is...
So you're saying that sin is widespread in the philosophy of physics? Yes, yeah, you're endorsing Joe's condemnation of my mentioning the marriage.
Something we ought to stop as a discipline. Here's the question. So this is, if you like, more philosophical, where you have this kind of new respect, and it links to the issue of whether it can be a defense of something like the cosmological principle. So I mean, this is incredibly fanciful, but suppose it's been cloudy for the last 100 years, and suppose that nonetheless, somehow, we pin down our choice between cosmological models to something which qualitatively looks like lambda CDM, and something which qualitatively looks like the model was going to be a limit atomic model, which details this don't matter. Given its cloudy, you can imagine the dialogue between these various people being something like, well, you know, we don't know at the moment, but the weather people tell us it's going to stop being cloudy in a year or so. When it stops being cloudy, we'll be able to look into the night sky. And according to the CDM model, the universe is homogeneous and isotropic, so what we should expect to see is that the stuff going on at large scales is pretty uniform. And according to the LTB theory, the universe is not homogeneous, and so basically what we should expect is to find that the universe is pretty highly ununiform, and we can go tell from an ununiformity how far we are from the centre. And then the clouds clear, and then we see that actually the sky is homogeneous. Now at that point it starts to look a bit desperate for the advocate of the other theory to say, well, our theory is looking just fine, just so happens we're in the middle.
Yeah.
I mean, a different way of putting that is the observed homogeneity of the universe is a priori another interesting and striking feature of it. If you want to explain that observed homogeneity from our point of view, one quite good explanation is to say, well, it's the general feature of the universe is homogeneous. Other than equal quite a bad explanation, it seems, is to say that it's inhomogeneous, but we just happen to be in the special place. Now, that's not to say it's going to be ruled out of court, and in particular, if you imagine that one looks rather carefully and discovers a little bit of inhomogeneity and says, okay, well, a little bit due north of the centre of the universe, then fair enough, that's a legitimate way science can go. But at least there's a kind of working hypothesis. It looks reasonable to say hypotheses that explain the homogeneity by saying we're in this special place, a little bit.
Totally agree, especially about it's been cloudy for the last 100 years. I mean, of course, it's the bad weather that prompted the development of radio astronomy. So we've got to look at the cognitive side benefits of our rubbishy climate. So I do agree, of course, low likelihood events cannot be parlayed up into being adequate evidence for the hypothesis which gives them low likelihood on the Humean rhetorical grounds that, well, something's got to happen. You know, why should I not be in the tail of the distribution? No, I didn't mean my low-key Humeanism to be desperate in the sense that you described the LTB enthusiasts being desperate after the clouds cleared. So I think I hope I'm getting your point, but I agree. Yeah. So the cloudy parable does make vivid the severe limitations, and we better be. It goes back to my word typical and the Copernican principle jargon. We better be not too low likelihood if this thing is to stay in the water.
Yeah. Tritypicality is a working hypothesis, you know.
Yeah.
When the evidence tells
Yeah. So in this sense, although I shouldn't have, when I was saying I was a bit dismissive of the rationalistic enterprises of appealing to Copernican principle, as a working hypothesis, it's mandatory, I'd say. Yeah, absolutely. Yeah. Sorry, John, and then Simon.
You didn't mention the other tool that we have in this game, and that is building very large simulations of galaxy clustering, expanding universes, and then you would be able to see what was the effect of small-scale clustering on your picture of the overall expansion. So this is something that increasingly you'll see more and more of larger, fine-grained simulations. So there's a way of attacking this sort of problem. Computation.
Yes.
And the other point.
So and the gist of the sorry, go on. Yeah.
The other point was that if you look at the density perturbation, the sort of over density on the length scale L compared to the mean, so sort of delta over rho, and this falls down as some power of L, then if that power is smaller than 2, so it falls off more slowly than 1 over L squared, then eventually, if you go to large enough scale, the universe will have to become non-Friedman-like, and the cosmological principle would not be true. But if it falls down more slowly than 1 over L squared, then it will become increasingly homogeneous and isotropic on larger and larger scales. If it's exactly 1 over L squared, then it has the same perturbations on every scale. And that's roughly what we observe.
Right.
And of course, the one that goes down faster than 1 over L squared, if you went to very small scales, it would also become rather non-Friedmanic. So this very special spectrum in between, with no preferred scales, is not surprisingly the prediction, basically, of inflation with small populations. Right. And if the steady-state theory that people had scratched their heads a few more times, they would have been able to predict that was the spectrum that the steady-state universe had to display, because no other spectrum obeys the perfect cosmological principle.
Right. That's very helpful. Yes. So we are in the happy place, but they would have been too. Yeah. But we observe ourselves to be. Yeah. So this is in a sense, and it's predicted by inflation too.
Yeah, and they both come from the sitters.
Yeah. But right. Okay. So this is partly okay. Thank you. Yeah. Simon. Yeah.
Jeremy, you've very bravely given a perspective on what philosophy of cosmology could be about, that should be about. I often wonder really what does the philosophy bring to the table in major field of physics, and sometimes I think really they bring simplicity to the table because we don't really understand sufficiently technical issues. We need to simplify somehow, and that is a virtue, it seems to me. One can't expose issues that tend to be glossed over. Another virtue, I think, is that philosophy tends to connect things. We could be doing something in cosmic space physics, but then only a philosopher will come along and say, what about my everyday experience? And what about, do you mean to say that me tomorrow is just as real as me yesterday? And physicists don't ask that sort of question. And yet I think we all respond to that. So I have a question for you. One thing that philosophers of physics do tend to do is focus on realism, and specifically realism and quantum theory. And that's something that cosmologists tend to run a mouth on. So, one might think that philosophers of physics, philosophers more generally, could bring to cosmology some bringing together of issues of realism and quantum theory and issues of the universe. So, what about solutions to the problem of measurement and cosmology? That hasn't figured at all in your talk, and I wonder, was that intentional? I mean, do you think it's right to stay away from the measurement problem? I just wonder what your take is on this. And I actually have the thought that, after all, of the three major solutions to the problem of measurement, all involve wave function realism.
Three major realist solutions.
Sorry?
Three major realist solutions.
Yes, the three major realist solutions. Of course, I do note that you're speaking to the OASIS group on Friday on another solution to the problem of measurement. So perhaps this doesn't catch you, but one might think that there's wide consensus that if one's a realist about quantum theory, then the wave function had better be something real, and one might think that that ought to be relevant to cosmology. So I just wondered.
Okay, well, thank you for that. In the spirit of this sort of Oxford tutorial for Butterfield, that everybody else is expense of their time, I would just say, in a family atmosphere way, that I agree. I think that philosophy of cosmology should engage with that, not just have an eye on it, because it is, as I understand it, it is central to the quantum fluctuations that are then the so-called seeds of later structure. And I noticed, speaking of the other realists than your Everettian good self, sir, here in this branch, no doubt equally good in your other branches. The pilot waivers, you see, Struve and gentleman in Rio, forget his name now, Nelson Pinto, I think, have given an analysis from the pilot wave perspective of how the fluctuations work. And I do think, and I noticed that Mukhanov book mentions, as does, I think, the Liddell and Leith book, that these issues have not entered the mainstream of physics, these measurement issues, but they admit for a paragraph that somewhere on page 200 in their highly technical analysis that there is going to be a quantum to classical transition here. So I think that is a very rich field for philosophy of cosmology, perhaps. So, but I don't know anything about it. Yeah. Okay, well, should we?
Our last question. We started 5 minutes late.
Okay, David?
I mean, just picking up on that, I mean, bear in mind that some of those solutions to the measurement problem change the equations in various ways that fit rather neatly into Joe's kind of 1% solution space.
Right, well, I shan't comment on that, except to admire your intellectual precision.
So, can we thank Jeremy?